I'm really glad you're here.
I just gave him a final exam.
Good. All right, good. So much of a better picture of Cisler than the one that we used to use. He was a pretty interesting guy. I read about him and his involvement in the war in the 1940s and his one of the founding members of the engineering academy. And he really was a pretty. But what was his connection with this institution?
Um, it was more of his connection with the Holly Foundation.
HOLLEY1.
HOLLEY1, yeah. So they are passionate about supporting educational initiatives.
Yeah, I looked at.
And so the grant that launched this lecture series was in honor of Cisler because we had at the time a Master's of Science Education program. And so it was Maria Vaz, I think, who was the initiator of that Master of Science Education MSc program when she was here as Associate Dean, actually, before she became Associate Provost. I think it was through her that the Holly money was secured. But the whole point of this lecture series was to promote science education. So the connection wasn't so much Cisler to Lawrence Tech, it was Cisler to the Holly Foundation and the Holly Foundation to us.
That was the sense I was getting, because I couldn't find any reference to Lawrence Tech in anything I read about.
On the other hand, I've also read, a bit about his background. It seems to me he spent an awful lot of time with Henry Ford connection. So Ford, of course, indirectly, yes. Yeah, okay, you mentioned the National Academy of Engineering. That's one of the things that I'm going to mention when I'm reading
But
about
I was
this.
president, I think the guy that was president, I thought I was thinking pretty well. We were deans together, and we would spend time every February. The deans would get together in Washington, part of ASI, and it was a good time together. He was president of IIT for a while, and he was dean of Carnegie Mellon first, and then retired and then became president.
Cisler was, according to what I read, one of the founding members.
Yeah. Yeah.
So we'll give him his due in short order.
It's a good idea. I think the Holly Foundation will appreciate that.
They're still in operation, as I understand.
They are. Yep, and we're still actually asking them for money. So
And quite focused,
to try to find some money.
from what I read on the Holly Foundation site, they are really focused on Detroit, Detroit area.
All right, everyone, we're going to get started. Thank you for coming out to the Cisler lecture tonight. I'm Patrick Nelson, the interim dean of the College of Arts and Sciences, and we're going to get started. Our provost, Richard Heiss, is going to give a brief introduction, and then we'll turn it over to a few other quick individuals to say some quick words and get on to our wonderful speaker.
Thank you, Dean. Well, first of all, welcome. On behalf of the president and the university, I'm going to welcome Dr. Brian Friedrich to our campus. I'm glad you're here. It's always a pleasure to have these kinds of gatherings, particularly when we have individuals talking about technical and scientific content. From one chemist to another, I'm really pleased that you're here, particularly in the College of Arts and Science. It's totally appropriate. And we'll be doing more and more of this as time goes on and the university continues to grow and develop in the pathway that we're laying out for it. So thank you for coming, and I trust you'll have an enjoyable evening. I'm confident that I will. So, Glenn, you want to, I think you're up next.
Again, welcome to everyone here. Just wanted to give you a little bit of background about the Cisler Lecture Series, and then we'll move on to our speaker. The Walker L. Cisler Memorial Lecture Series, which is free and open to the public, was founded at Lawrence Tech in 1995 with a generous gift from the Holly Foundation. Well known for his leadership of the Detroit Edison Company from 1954 to 1971, Walker L. Cisler enjoyed a career that spanned a lifetime of personal, professional, civic, and business accomplishments. As an international ambassador for the American electric utility industry, he worked closely with heads of state, both here and abroad. As a tireless, dedicated humanitarian, he strived to improve the quality of life for people everywhere. Among his many notable contributions to society, Cisler was a founding member of the National Academy of Engineering. He also served as director of the Thomas Alva Edison Foundation, an organization dedicated to inspiring and rewarding an interest in science among youth. The Walker L. Cisler Memorial Lecture Series honors his legacy by promoting the improvement of science education for students of all ages. A quote from Mr. Cisler that aptly summarizes the purpose of the lecture series reads as follows: "Science, engineering, technology, and accordingly the country cannot prosper until we once again produce a truly scientifically literate populace." So thank you for coming. Now I'll turn it over to you, Nelson.
All right, thank you. So I have the honor of introducing our speaker, Dr. Amanda Bryant Friedrich. She is the current Dean of Graduate Studies and Professor of Pharmacy and Health Science at Wayne State University. Comes to us with a very diverse background. Went to undergrad at North Carolina Central University, which I've been on their campus giving a talk many years ago. Then went to, which is an HBCU, and then went completely different just down the road to Duke University, because they're two very different universities, because I was at Duke also. And then ended up at Heidelberg University for her PhD. Heidelberg is one of the oldest universities in the world, actually is the oldest university in Germany, so a little bit of tidbit about that. She's a 2014 American Chemical Society Award winner for the advancement of diversity in chemical science, fellow of the American Association for the Advancement of Sciences, and an American Chemical Society. She received the NSF Career Award in 2003, a very tough award to get, I know. I tried and never got one. And if you go on Google her, which my wife hates it when I say Google her, but she's given some wonderful TED Talks, okay? One of the TED Talks is seeing myself in my science teachers. Okay, so now her talk today is on an organic chemist's role in the elucidation of the endogenous exposome. So please welcome Amanda to give our speech. Thank you.
Thank you so very much for the wonderful introduction for the history lesson on Dr. Was he Dr. Cisler? No? That's interesting, because I was wondering about that as I was doing research. He probably did. I am very, very honored to be here today to give this lecture. And to be honest, this is my favorite place to be. Whenever I'm talking to, not saying anything bad about the faculty, but I see students. And I'm so excited when I get to see students and I get to talk to you. I don't like to give lectures in that sense. I like to have conversations. And so I'm hoping that during the time that we're together here, we could have a conversation. And we're going to have a conversation about some organic chemistry. Around that time, you guys are going to start getting like glazed over. And then I'm going to start talking really loud so that you'll stay with me. But we're going to talk about a lot of other things as well today. So the first thing that I wanted to show here was another quote that I actually found from Walker Cisler. And I found this quote to be so fitting for today. And I am going to read this, and I want us to really think about what it's saying. This 1 gram of uranium can provide the same amount of the energy that comes from 3 tons of coal. Coal is the energy dug from the ground, but nuclear power is the energy dug from human brain. Countries such as Korea that are poor in resources should develop the energy that can be dug from human brain. If you want to operate a nuclear power plant, you should develop human resources first. If Korea brings up the young talents now, then Korea becomes the country that can turn on electric lights from nuclear power 20 years later. Now, he said that a long time ago, and we're still in the same place. We are still in the same place because we have not recognized as a country that the most important resource we have is human. Our human resources in the United States of America are diverse. They are strong. We have the resources to train people in anything, but we haven't done a very good job of doing that. And so here I have a slide from the American Physical Society that shows where we are when it comes to science and women. And I'm focusing on women because it's easy to remember that women make up 50% of the population, right? We remember that, right? 50%. And we can pretty much agree on that. When you look at the slide, you see there that it actually shows that women get about 50% of the PhDs, right? That's up here. Right there, you see that? Women get approximately 50%. Biology, women get more than 50%. You see that? But let's look at some other areas, okay? Physics. Ooh, sorry, I don't want to yell at y'all too much. No, don't let me do that. Physics is all the way down here. Why is it that women are not getting PhDs in physics? That's the question of the century, right? Why are women not? Why are African Americans not? Why are Hispanics not? We keep asking the same question. Y'all can fill in the blanks. And we don't have an answer. And we don't have an answer. And I have dedicated my career, a long time now, the gray hairs are real, to trying to figure out the answer to that question. And the way that I've done it has always been through my science, always. And so when we think about then, who am I to be concerned? And who am I to care? I think you need to know a little bit about me. And so I'm going to tell you at the beginning of my talk about my scientific background. And then I want you to think about, as I'm going through the science that I'm going to talk to you about the endogenous exposome, I want you to think about how in the world did I end up being where I am now. I want you to think about it. And then we can have a conversation. So as the interim dean said, I went to North Carolina Central University, which is a historically black college in Durham, North Carolina. How did I end up there? That's an interesting story as well, I won't tell you. But every phase of my career is grounded in an organic molecule. And so here you will see that the first molecule that caught my attention was an indole. And you might think to yourself, what were you doing with that? Well, if you've been listening to the media and learning about historically black colleges and universities, they have been historically under-resourced. So my research advisor at that time, and they are very much PUIs at that time, North Carolina Central was very much a PUI, predominantly undergrad institution. He was working on making compounds that were anti-cancer drugs. And he gave me this compound and told me to go brominate it. Who in here knows how to brominate an aromatic ring? Lord have mercy, we're gonna have a chemistry lesson here. Thank you. Thank you. Well, I was doing my brominations on the bench top, not in a hood. And I thought it was the coolest thing in the world. It was awesome. It smelled like a pool because bromine smells a lot like chlorine to me. And I just thought it was cool. And I fell in love with chemistry then because I was adding my bromine to my reaction. Bromine is dark brown, and it was just going away. So I was getting that visual effect. Stuff was happening. I was sold from the very beginning. After getting my undergraduate degree, I went to Duke University. Duke University is by the greatest measure not a historically Black university. It is a very privileged, affluent university that has done amazing things. I'm very proud to be an alum of Duke University just as much as I am to be an alum of North Carolina Central University. And during that time, I was working on this weird compound called a phospholindole oxide. And I wrote a whole thesis on that and never did anything else with it. But the one thing that you should recognize is that I am an expert in aromatic compounds because I was doing indoles and then I did phosphoryl oxides, which are also aromatic. And then I left the country. And one of the things I remember the most about leaving the country was sitting on the tarmac and watching my brother through the window. He was standing there watching the plane. This was back in the day. The babies in here may not even remember it, but you could actually go to the place where the plane was. So he was watching me there. And I left the United States. And when I left the United States, I had no intentions of coming back. I was going away. It had been a long enough battle in science and in life, and I was like, I'm leaving. And I went to the University of Heidelberg, which is one of the oldest institutions in the world, has incredible history there, and I worked on another aromatic compound. And this is 1,6-methanocene-annuline. So yes, I did have to learn how to speak German. So I did that too. 1,6-methanotenannuline. And so this is a molecule that became my best friend for about 3.5 years. I got my PhD in about 3.5 years in Heidelberg. After I finished my PhD work, I still didn't want to come home. And so I started looking for a postdoc. And I decided through relationships, and this is the important part about remembering networking, sponsorship, advocacy, all of those things, relationships led me to my postdoc, which was in Basel, Switzerland. And so I worked then there for 2 years. And that was an incredible experience because I was working in a city that was full of pharmaceutical industry. And at the end of the day, that's what I wanted to do, or I thought I wanted to do. But you don't always know what's going to happen, right? So I started working on then another aromatic molecule, even though we don't think of it as aromatic, but DNA is an aromatic molecule that just happens to be connected, lots of aromats connected by sugars and phosphates, right? So that's what I did. And so the work that I was doing there actually is the one that kind of settled into my brain as to the work I wanted to do for my career. But everything I did up to that point has continued to support the work that I do. And I came back to the United States after spending time in Switzerland because I knew I had to. I didn't come back because I wanted to. I came back because I felt like I had to. My dear husband, who I've been with now for 30 years, reminded me that there are very, very few women with your background and who look like you who are PhDs in chemistry. So you owe your country, he's German too, I don't know what's wrong with him, to go home. So I came back. And where did I come back to? This is going to be interesting. Wayne State University. I came back to Wayne State University. And it was the two-body problem for those out there who are thinking about the issue of marriage and family and career. My husband is also a PhD chemist and is a professor at the University of Detroit Mercy. So one of us had a job, the other one didn't. I was the one without the job. I ended up as a lecturer at Wayne State. It was a transformative experience. I will say it that way. It made me realize what I wanted and what I did not want. And sometimes those things have to happen. That is what I figured out in life during that time. Those things have to happen. I ran away from there. I did. I was teaching lectures of 250 students in organic chemistry. I was barefoot. I'll tell you the truth. I hated wearing shoes. I still do. And when I had to teach those classes, I was up on a stage like this, and there were like 250 kids in the audience. And I just take my shoes off and lecture. I still have, there are physicians in the Detroit metropolitan area that if you mention Dr. Brian Friedrich, they will start laughing because they had organic chemistry with me with no shoes on. Okay, just remember that. So then I decided, I want to teach. I want to be able to teach people that I can see their faces and they're not little dots. And again, relationships, networks, advocates, mentors told me, well, Oakland University might be a better place for you to go. And so I went, I interviewed, I became a tenured professor there and gained tenure and all of that kind of stuff and had a ball. I mentored probably 75 to 100 undergraduates there in my research lab, mentored PhD students, got my career award, all of those kinds of things. But then, as life would happen, I was like, something's not right, something's missing. I want to do something else. I'm very restless, you'll be able to tell that story. And so I decided to move to the University of Toledo. How many of you guys have been to Toledo? Yeah. You drive through Toledo anyway if you're going somewhere, right? It was a wonderful experience. I was at Toledo for 12 years. I taught pharmaceutical sciences, so I went back to my roots. I have a PhD. Actually, I have a doctoral in pharmaceutical chemistry, so because I have a German degree. And so I went back to my roots, taught PharmDs, taught medicinal chemist, did all of that kind of stuff, had a ball, traveled internationally to recruit students, became a director of, what do they call it, International Graduate Student Recruiting and Retention, enjoyed it. The new president comes in and says, Amanda, you've been working hard for graduate students. Why don't you become the graduate dean? I was an associate professor, so my faculty colleagues in here know. I had never been a chair. I had never been an associate dean, and she wanted me to be a dean. I became a dean, because when the president says you're going to become a dean, you're going to become a dean. And I became also a vice provost. I did that. I did that for, I think, 6 years maybe, something like that. And then I moved back to Wayne State University. Exactly 20 years from the time I left, I moved back. Everywhere I've been, I've done research. Even when I was a lecturer at Wayne State at the very beginning, I had a hood and $1,000. So I did some research. You could do some research with $1,000 on the hood. Because remember, I started out in North Carolina with no hood, indole, and bromine, okay? So you can find a way to do your research. Now I am doing antiviral drug discovery and a lot of other things. And I included this picture on the screen because one of your former students is actually in that photo. And I am not going to try to find her here because it would take me forever. But Morgan Minieres was a student here and joined the PhD program in pharmaceutical sciences. She called up the grad dean. I don't even know how she found me, but she called me. She said, I want to go to Wayne State. I said, well, come on. She said, y'all got any money? I said, yeah, I got some money. And she has done fantastic there. So, having said that, then advocate for yourself. You want to go somewhere, call up the grad dean and say, y'all got any money? And if they say no, say, oh yeah, you got some money, go find some. So now I'm going to switch a little bit here and start talking about the chemistry. So I am by training everything foundationally an organic chemist. And so you're going to see that in the fact that I'm going to show you a lot of structures. And we're going to talk about some organic mechanisms and things like that. How many of you guys have taken organic chemistry who are students? Okay, all right. So if I ask you what's a radical, they shook their head before I could even ask the question. What's a ketone? All right, we good. Are you in? Oh, you. All right. So I'm going to do this the right way, and we're going to talk about some of this stuff. So we're going to talk about the endogenous exposome. And I love this quote, actually, from Jane Goodall, where she says, you cannot get through a single day without having an impact on the world around you. And, of course, she's a very strong environmentalist. But I want to make you remember that you cannot get through a single day without the world around you having an impact on you, right? Every time you walk outside of the house, the environment has an impact on you. When I came to Wayne State, I learned about the built environment. That's a term that we use very often to talk about the cement, the structures, the built things around us that have an impact on us. If you grew up on a farm like I did, you don't have the same environment, right? So there are some very big differences. And when we talk about the exposome, we're talking about a lot of different things. But I want you to just look at the very top here. It says it's defined as the totality of exposures. So everything to an individual is subjected to from conception to death. That's why you guys have this wonderful, I showed a pregnant lady because I couldn't find a single picture like this to show the pregnant lady. So I put her on. And then I decided not to show the casket because that was just too morbid. So we're going to go with the beginning, but we're going to think about the end different. And these include things from environmental agents, socioeconomic conditions, lifestyle, diet, and everything that's going on inside of your body while you're sitting here listening to me, okay? When you think about socioeconomic conditions and lifestyle, do you think about the connection? Think about the connection. I want to see some heads nodding. If you're growing up in a household where the income is $250,000 a year, then your lifestyle is going to be considerably different than if you're growing up in a home where the income is $50,000 a year, right? Well, let's go the other way. If the income is $10 million a year, right? The lifestyle is very different. So think about that then when you think about looking at this continuum of life from conception to death, how those things interconnect with each other. So what is the exposome? So there are three general areas that we speak about: the general external, the specific external, and the internal. So if we talk about the general external, you'll see there social capital, education, financial status, psychological and mental stress, urban versus rural, environmental, and climate. That climate word right now is the only thing that the EPA and the National Institute for Environmental Health Sciences is thinking about, because they believe that climate is going to impact everything else. Y'all agree? You agree? If it starts to get real hot in Detroit in December, you're going to see a whole lot of stressed out people, aren't you? Yeah, exactly. Do you think a lot of people are going to move out of the city and go to the country? Possibly, right? So if you are interested in anything that has to do with the environment, start reading about climate. I don't care if you believe in climate change. That doesn't matter to me. I want you to start reading about climate. I want you to understand what climate means, what it means to water, what it means to us, what it's going to mean about the insect population, what it's going to mean about viruses, what it's going to mean about everything. It's going to impact everything. So you need to look at that. The specific external then talks about things like radiation, and the namesake for the lecture worked in nuclear power. So that's all about radiation and understanding radiation. And so when I saw that today and I was reading about him, I was like, oh, so we connected over 100 years in thinking about these things. Infectious agents, viruses, bacteria, fungi, all of those things. Chemical contaminants, you see the rest. The one thing that people forget about is medical interventions. What are medical interventions? Taking medication, going and getting a CT scan, going and getting an X-ray. All of those things are part of the specific external. And then when we talk about the internal, then here comes all the biochem and all that kind of stuff. Metabolism. Have you guys been hearing all of the language and all of the talking around the gut microbiome? You know about that? And then the oral microbiome and all of those things. A lot of stuff about metabolism. And we're finding the chemical compounds that make up that microbiome. There are chemical compounds in there. We have to think about that. We think about lipid peroxidation, oxidative stress. Anybody ever heard of oxidative stress? Does that say anything to you? Okay. Y'all take your vitamin C. See, I know you smart. Look, she's taking her vitamin C. Who else taking the vitamin C? You need some antioxidants in your life because that's part of what the internal is. Pardon? Oh, you eat it. Exactly. I love that. That's right. Okay. I skipped the slide. There we go. So I want you to think about, as I talk about the chemistry that I do, you're going to see some things that are related to lipid peroxidation, inflammation, and oxidative stress. My work is also related to radiation and diet, but I won't point that out as much today. So this is a very interesting graph that I'm not going to try to go through because it's kind of weird the way that they put it together. But it's about total exposure, because remember when we're talking about the exposome, we're talking about total exposures. And what you see here are some of the things that they looked at in blood. So they call it the blood exposome. And what you want to see here is there are pollutants in the red line. There are drugs on the black line. Food products are the gray, and blue is endogenous. Okay, so I think about endogenous a lot. So if I look at that, there's estradiol, testosterone, cortisol, malondialdehyde, homocysteine, and cholesterol. Those are all molecules that are found in your body and in high amounts, because this total line basically is 100%. So if you go from estradiol to testosterone, that's a certain percentage of the sex hormones. And then you're going from testosterone to cortisol, that's a percentage of the total from here to here. Malondialdehyde is very important, and we're going to talk about that one in a second. But you can see cholesterol is an important thing that we have that's endogenous and is part of our exposome. So we have to have it, and we want to think about that as well. You'll see here also, if you're looking at this and you're interested in drugs, the blood exposome, and they looked at a lot of patients to determine this. You can see people take a lot of aspirin, simvastatin. Does anybody know what simvastatin is? Yes. What is it? Cholesterol drug, exactly. So a lot of people taking that. And all of the drugs that we actually know are out there, you can see here that there are only a few that end up on this cumulative percentage diagram. So this is malondialdehyde. It's a very small molecule. It has 2 carbonyls in it. They are both aldehydes. Did you learn something now? Okay, aldehydes, all right. 2 aldehydes over here. And they result from a process called lipid peroxidation. And these are the lipids, of course, that make up the cell wall that have many different functions. And you can see here, this is a radical, okay? A radical is a single electron that is not bonded, that is extremely reactive, and whenever they form, usually the first thing that happens is they get trapped by oxygen, because our bodies are saturated with oxygen. Then you get something called a peroxyl radical. The peroxyl radical then will degrade and finally give you malondialdehyde. So my organic students, is this reactive or very unreactive? What you think? Reactive or unreactive? You can guess. Is it reactive? Say yes. It's very reactive. Yes, applaud. I like that. It's very reactive. You guys got it. It's very reactive because it's a dicarbonyl, okay? And it's reactive towards what? Nucleophiles or electrophiles? Very good. Awesome. Yes, nucleophiles. And so the body, in the cell, we have lots of nucleophiles. So this thing it can react with a lot of things. It can react with proteins, it can react with DNA, it can react with RNA. And so that's why it becomes an issue. And you will see here that it can also form from other things, including DNA. So this is just thymidine in a DNA strand. There's a radical formed here. Basically, radicals form in these ways by something coming along and removing a hydrogen atom, right? So you have a radical here, it reacts with oxygen, you end up again with something that becomes a peroxyl radical, or a hydrogen peroxide in this case. Then it degrades to all of these compounds, including malondialdehyde. So we have two different sources that we know of in the endogenous exposome where malondialdehyde forms. And they then react with DNA molecules to give us products here. You can look at this and tell, even if you've never looked at DNA, this does not look like that, does it? No, this does not look like that. These are called DNA adducts. And DNA adducts will actually change how your DNA is read and can lead to the development of cancers and tumors and all of those kinds of things. So what we're saying here is that we have something in our body that is formed in our body that can go on and react with DNA and cause DNA damage and is carcinogenic or tumorigenic. That's what we're saying here. The other one is acetaldehyde, and acetaldehyde also can be problematic. But this is the one that we've looked at in our lab. So my work in my lab takes a concept of developing tools. Because remember, I'm a synthetic chemist, so we develop tools, and in this case, we're talking about developing tools that help us understand the rules of life. And the rules of life have to do with what happens to these small molecules when they form in a cell. So my nucleic acids toolbox looks like this. These are the molecules that we made over the years. I think that's the last one, yeah. And you can see here in the center, I have a piece of duplex DNA, and I have an eraser there. Because what we basically do is we put on, what's this functional group, organic students? Y'all just told me you knew what it was. It's a ketone, exactly. I love it. So we put these keto groups on. You see that we use those a lot. And we put them on a very specific location in the DNA, and that allows us to create a radical at that spot in a piece of DNA so that we can determine what products form. So that's our toolbox. We also use phenylselenides, which is something that I won't talk about much here, but these compounds also, we use them to generate radicals. And how do we do that? With the ketones, we use a process called Norrish type 1 photocleavage. So in my laboratory, we have a very strong light source, and we do photochemistry. So we can expose a piece of DNA that contains one of these carbonyls. It will then, what we call photoexcite the carbonyl or the ketone. It loses carbon monoxide, and we end up with two radicals. And those two radicals come from here, cleavage of this bond and cleavage of that bond. So we can do that anywhere we put in a keto group. We have done this over many different kinds of molecules, of DNA molecules. And so what we have to do is we make the monomer, and then we actually put on these different groups. We put it onto a machine called an automated DNA synthesizer. We can synthesize any strand of DNA that we want to, and we can then actually, place that into duplexes, single strands, all kinds of architectures, we call them, to study what happens in a realistic system when that radical is formed. We do product analysis using ion exchange and reverse phase high performance liquid chromatography and Multitoph mass spectrometry. So that's how we determine what we make, and if we want to know how much, we use ion exchange reverse phase high performance liquid chromatography as well. So this is just one of the radicals that we form. This is thymidine. The radical formed here is at the C3' position is what we call it. It undergoes oxidation. This is under conditions of no oxygen. And we know our cells are usually oxygenated, but one of the hallmarks of cancer cells is they have very low oxygen levels. So we want to know if this radical forms in that situation, what happens. So it undergoes an oxidation. This is the solvolysis. You guys remember learning about those elimination reactions where you form carbocations? That's organic 1. You good? Y'all good? Remember that carbocation? I'm looking at the person with the gray sweatshirt on with the hood on. She's looking around. It's you I'm talking about. You didn't take it yet. Oh, man. Do you remember the carbocation? So you do solvolysis, you get a strand break. That's the erasure that you saw in my DNA. And then you get these small molecules here. And this is the one that I wanted you to kind of see here. This is a small molecule which has a carbonyl group and double bonds. And it's extremely reactive, extremely reactive. And we can also have chemical repair. So this is here. So this is the kind of work we do in that respect. We also make these substrates so that we can follow the processes. So we identify here that this is one of the products that forms from this radical. So we decided to make it ourselves chemically so we could study how it behaves. So that's what we did there. This is some data from LCMS. These are liquid chromatograms. We can actually see mechanistically, once we form the ketone, what happens to it. So we see we get a double bind here, and we actually get a fragment here. That's the erasing again. And that is our actual way of determining that. The next thing that we have to remember is that nothing happens in the cell by itself. The cell is crowded. It's very crowded. It's crowded with proteins, antioxidants, cofactors, everything. So the one thing we wanted to know, if this small molecule forms, is there anything in the cell that can react with it? Well, our cells love to use thiols as antioxidants. And so we looked at it then to determine if this molecule would react with thiols, and we found out it did. So we know that there's a way to get it out of the cell that is available to it from just simple antioxidants. When we add oxygen to the equation, then you see those things that we talked about before. You get a hydrogen peroxide, but you still get this 3' ketone. And so we're making the same molecule again under aerobic and under anaerobic conditions. And I'm not going to talk about this because this is at a different position, so I'm going to move through this. We also do the same kind of work in RNA. That was what I wanted to show you too. We've decided to work on small nuclear RNAs to try to understand cancer development and if it's related to oxidative damage to these RNAs. We know that this RNA has a modified nuclear base in it called pseudouridine. So we're working with that molecule, and we're developing the same kind of concept as before. You can see here this is an RNA because it has an OH here. We make radicals, same kind of intermediates, and we can follow them to see what they degrade to. That's the work we do. And there's that ketone again. So we do a lot of chemistry to make ketones. And interestingly enough, for anyone who's ever done synthesis, you know that just by adding another OH in this molecule, the synthesis becomes completely different. So every student who comes to my lab has to learn how to make something to blow it up. That's how I sell it. So if you're interested in making stuff and want to blow it up, come talk to me. We do X-ray crystallography to actually look at the structure of the nucleosides that we make because we want to know what they look like before we put them into our DNA and RNA. And let's see here. One of the most important discoveries that we made with this work was in the case of the ketone here, we photolyzed it, we get the radical, and we found that it does an internal reaction, which no one had ever observed before. Now, when you find something in your research that no one ever saw, you go home and do the happy dance. The only thing is that you guys see is unpublished results. I need to publish that paper now, so that's the important part, right? So we see here, we get this cyclo compound. If this is formed in RNA, it's going to have a huge consequence on the actual structure of the RNA. And that is something that's very important, and that's what we're working on now. So, when we talk about looking at the constituents of the endogenous exposome, what we've actually found is these are the ones that we have determined from the work that we've done. I didn't talk about all of these, but you saw this one, and you saw this one. So we know now that we actually can determine and measure the amounts and determine the reactivity of these molecules. And that's where we are now. Because just by identifying it doesn't tell us anything. But we need to find out, does it react with proteins? Does it react with DNA? Is it carcinogenic or any of those things? And how is it metabolically handled by the cell? So, yeah. So now I'm going to switch back again. You guys thought about my academic training. You saw the science that I do. Okay? So now who am I? That's the next question. Who is this person standing here? Well, this is a house very similar. I do not have a photo of the house that I grew up in. But this is a house very similar to the one I grew up in North Carolina. Okay? And we did have a dog. People always ask me, did you have a dog? Yes, we did have a dog. No indoor plumbing, no HVAC system, and no telephone. Okay? I was born in 1968. For the babies, they're like, she is old as dirt. For my colleagues who may be closer to my age, you realize that wasn't that long ago, right? Right. Segregated South still, actually, to be honest, because my best friend happened to be the only white girl in my class, and she and I would go to the doctor, and she would sit on one side and I'd sit on the other side because it was still segregated. Okay, so that's how I grew up. And one of the things that was clear to me very early on is that I was swimming upriver with everybody who looked just like me. We were in a school system where 98% of the kids were African American. So everybody looked like me. So it's just like often when I talk to students who come to the United States from Africa, they say to me, we don't think about race because the race of everybody is the same. And so it was kind of like that in my school. We didn't really think about that. Then I went to North Carolina Central University. Same thing. Then I went to Duke. But y'all noticed I was swimming out front, right? Okay. But let me just say something that's critical here. You guys have heard me talk about mentors, advocates, sponsors, all of those people in your network. Well, some of them look like me and some of them didn't, because some of those people still are swimming right there. They are part of my network, still part of my network, okay? Most important part of my network is the challenger, the one who texts me and say, Amanda, you need to take off your Superwoman boots. She says I wear Superwoman boots because I'm always doing too much. And go rest. So you need to have that. Oh, why does it keep doing that? This is when I was in the Middle East recruiting students. This is when I recognized that I knew who I was, because I could go into an environment where I had been told many things about what the women were dealing with there, and I could listen and hear it for myself. You can see me there. I'm in a hijab and an abaya. I was in Saudi Arabia. I had no other choice. But it was comfortable because I was there on a purpose. I went into rooms where there were young women who would walk up to me and thank me for being there because they said they had never seen a woman in my position before who would come and dress like them to speak to them. So I'm telling you this because you need to meet people where they are. You don't try to convert people to be like you. You meet them where they are. While I was doing all of that stuff, I married that great guy who's standing there in his tux. It's my husband, Klaus, who some people in the room know. He's a professor at University of Detroit Mercy. We've been together for 30 years. We met in grad school. Making the decision to marry was difficult for me because I never wanted to. But the universe decided that he was great and I needed to marry him, so I did. And then I didn't want to be a mom. I was like, all of this stuff is getting in the way. Then I had Klaus, who's over there on the bike. Klaus is 22 and a senior at Wayne State. And then when I was 42 years old, Lord have mercy, came Cornelia, okay? Exactly. And that's my sweetie pie that's down there. I decided at some point that I wasn't going to let the norms of society dictate what I do. That is exactly what happened, and that's why at 42 years old I was crazy enough to have another child. But anyway, while I'm doing all of that, I still do this. Dr. Collins and I probably need to go and meet out in some of these outreach activities. This is what we do. We do this on the weekend. We do this at 7 o'clock in the evening. Why do we do it? Because look at those faces. If we're not there, who's going to do it? Right? Make it part of your mission. Because you're here. You have the privilege of being here. Make sure somebody else can come and sit in that seat when you're gone. Okay? So that's what we do there. This is about personal identity. And I was at Pontiac High School today, and I had a group of 60 young women today. Yesterday, I was there with 60 young men. And the one thing that they picked up from me that I found out was the fact that they needed to realize that they couldn't let other people tell them what their life should look like. Because a lot of us go into schools and we tell every kid they need to go to college. Does every kid need to go to college? No. They don't. Because just like I said when I was in Saudi Arabia, we need to meet people where they are. And if a student says to me, I want to go be the best HVAC technician that you've ever seen, I'd be like, thank you, because I need somebody to come to my house right now. So we have to encourage. Yes, college is wonderful. I'm a grad dean. I want everybody to get a PhD. But that's just not everybody's journey. And so this is what I talk about, going through birth, the events, now life stages, plans, we eventually die. But experiences and plans is what dictates everything that happens, right? So that's kind of it. All of the work that I have done, scientifically, outreach, diversity, all of that stuff has been supported by all of these folks right here. The National Science Foundation has been my best friend. You'll notice that the National Institutes of Health is not on there. And so that's my holy grail, actually, before I retire, is to get an NIH grant. I run several, but I've never competed for an NIH research grant, and that's what I want to do. So I still have my own goals, recognized. I've contributed to all these books, just books. If you ever want to read about building your best chemistry career, I'm in that book. If you want to be a mama and you want to be a professor, I'm in that book. If you you want to read about black women who are chemists, I'm in that book. But the stories, the narrative around becoming is very important. And this is not just for women. It's not just for minorities. Y'all white dudes in here, y'all need to think about this stuff too, right? Okay? And talk to some of these women in here because they'll help you figure out your way. That's what we do, right, ladies? Okay. These are some of my students, the work I talked about today. Dr. Mel Betty, the one down with the pharmacy badge on his shoulder, is the research assistant professor who runs my lab on the day-to-day. Dr. Betty is originally from the Ivory Coast and has a PharmD and a PhD, and he got his PhD with me. And thankfully, he moved with me from Toledo to Wayne State to continue my work. Those students up there in the corner, Brandy is the one over here. She just got her PhD on Friday from the University of Minnesota. I'm so excited. Hans in the middle got his PharmD and will be graduating in a month or so. And Immaculate, she got her PhD with me. Saad is from Saudi Arabia. He got his PhD from the University of Illinois at Chicago. Nicholas Amato, the one down there playing the instrument, is a scientist at Moderna. So we had lots of wonderful conversations during the pandemic talking about the science. And yeah, I make oligonucleotides, and that's what the vaccine is. So we had great conversations. And he's one of the, Moderna has a very interesting concept. Each employee has a number. He's within 0 to 100, so he's one of the foundational employees. And then Akrima is from Indonesia, and she is now back there as a professor. So, thank you. Any questions?
We have time for questions. Sabrina, we need the microphone. Got it. They need it for the recording. I can hear you.
That was a really great talk. My question, though, is about the selenium compound that you had there. So I'm curious because as we chemists, we find one element on a periodic table and we want to see does it behave like another element. So with that particular compound, I'm just curious if you've done a similar reaction with sulfur.
Ooh. So photochemically, if we use just the thiol, we don't get the same photochemistry. We have to oxidize the sulfur. And we can do photochemistry there. Selenium, the carbon-selenium bond is not as strong. So photochemically, it excites and breaks faster than the sulfur-carbon bond. But we can do the same thing if we oxidize the sulfur up to a different oxidation state. So yeah, that's a great question. Thank you.
Questions? Some of the students, it's your turn to ask her some questions. What you want to learn? Come on, you're ready. Questions?
I'm an open book.
Here we
You
go.
can ask me anything.
All right, we got a couple questions.
Oh, you have on a North Carolina shirt.
Oh, I'm not from there.
That's okay.
Yeah.
You're still showing love.
What motivates you?
You. It's you. It is definitely you. My motivation every day to get up is because that I know that I have the resources. I'm a human resource that can help you get to where you want to go. I make myself incredibly available. If you go to my LinkedIn page, I have thousands of people who are following me or connected with me on LinkedIn, and they don't hesitate to ask me a question when they need mentoring. So that motivation comes from that. And then those little people that I showed you, my husband, my son, my daughter, they motivate me in ways that no one else can, just by being a wife and a mom. Great question.
That
Thank
is true.
you.
Doctor, thank you for coming. How has technology, or specifically artificial intelligence, changed your lab, what you do, and what would you say to these young students? Should they dig into this area with all the principles and the basics that you know, right, from the training you've had many, many years without technology? Is this something that they should also be looking at?
Oh, that's a fantastic question, and I will tell you the absolute answer is yes. If you have the opportunity to learn about artificial intelligence and machine learning, you should. And it's interesting you ask that because we have a paper that's about to come out very soon that we worked with a company in California who specializes in using machine learning and artificial intelligence to look for new antiviral drugs. And because my laboratory knows how to make a lot of things, that's what we specialize in, we partnered with them. And we took fragments that they had recognized through artificial intelligence. We made them, we tested them. So the artificial intelligence doesn't get rid of the person, right? The machine learning, the artificial intelligence can give us a set of compounds, chemical compounds that we can look at. But in the end, we have to make them, we have to test them. So what do you need? You need the basic understanding about chemistry, right? Because you need to know if they put a sulfur and a selenium next to each other in the compound, you need to know that it's not going to do the same chemistry, right? So you need the basic understanding. But the machine learning is going to make your life so much easier. Because drug design for me was what we used to call ethyl methyl propylbutyl. We would go into the lab and we would make a compound, we put a methyl group on, an ethyl group on, a butyl group on, and then we test all of them. Now we can do that with AI. So it's a fantastic question. So we're moving into a new era. And I think in any discipline, English, sociology, chemistry, engineering, all of it, you need to know something about AI. You're welcome.
One more question. Actually, one or two. No, we can go two. I'm just.
Sure. I'm in the biomedical engineering department, and I see a lot of our students here today.
Yeah.
What's something a biomedical engineer who's trying to take maybe some of the tools that you have been working on in your lab and applying them for medical devices or medical design, what's something that they could do right now, maybe in their studies, that would make, when they are eventually on a team with the chemist, what's something that they can work on to make sure that when they talk to the chemist doesn't rip their hair out?
I think one of the things that would be great there is to learn about toxicology. And because biomedical engineering, you're making a lot of things that are going to interact with the biological system. And we don't understand enough about the toxicology related to some of those interactions. If I'm standing here and I'm talking to you about, and I'm thinking about medical devices in particular, one of the things that I worked with some folks when I was in Toledo, just looking at how devices are put together, especially the ones that are internal, and how the chemical constituents of the device can lend itself to being toxicological for the person. So understanding toxicology is a place where I feel like we very often don't speak the same language. So I think that would be a great place to start, is just looking at that, because devices also have inorganic compounds in them sometimes, things like that. Inorganic people talking to biomedical engineers, talking to toxicologists, is like, we don't speak the same language. So I think that would be a great place to start. I think he agrees with me. Y'all think he agrees with me?
Mm-hmm.
I love it.
All right, any other questions? No? All right, yes. One. We need to have one of these balls that they throw. I've seen this at another place.
Oh, I've seen those. Those things scare me.
I just wanted to ask what's special about ketones that's not with other carbonyl compounds? Because you are doing mostly with the ketones.
Oh, why are we using ketones? Because that has to do with the photochemistry of ketones. So there are several reasons why we use ketones very specifically for this application. They absorb light at 320 nanometers, which is outside of the range of other biological molecules. So if we want to photolyze a system, we can't photolyze a system where other things would be absorbing. So that's number one. Number two is that you can photoexcite the carbonyl and actually cause that Norrish type photocleavage, which you can't do with any other functional groups at all. The only functional group that does the Norrish type photocleavage is the ketone. There are two different Norrish type photocleavages. There's a separate one, but it's also a ketone that has to do that too.
Not even with aldehydes or?
No.
Okay.
The difference with the aldehyde is that you have to split a carbon-hydrogen bond.
Mm.
And we know how tight that bond is, and so that's the reason why. So that's why ketones. Thanks, great question.
All right. All right, thank you everyone for coming out. Amanda, thank you for an amazing talk.
Salisbury?
Are you serious?